Okay, so in this video we're going to look at two problems where we're going to be using the dot product. Our first problem is we're given a cube and we want to find the angle between one edge of the cube and the diagonal that starts at the same initial point as the edge. So imagine that they start at the same initial point here. You pick an edge and a diagonal, okay, that starts at the same place, and you want to find the angle between these two line segments. So how are you going to tackle this problem? Okay, we're going to use tools from this section, and one thing is we can associate to these line segments vectors, and then in that situation the problem will just become finding the angle between two vectors. So the first thing is to set up that cube in 3 space. So we're going to create axes like this, the x, y, and z axis. Remember, the x-axis is kind of like coming towards you, okay? So the z-y axis is this screen, and x is coming at you. Now I'm going to draw my cube. Here we go. I'm going to add the edge and associate to it a vector. So the natural vector to construct is the one starting at the origin, ending up at one of the vertices of the cube, and I'm going to add the vector which describes the diagonal, and we want to find this angle here. So we need to associate coordinates to these vectors, because what I want to use is the dot product, more precisely the fact that the cosine is the dot product between the two vectors divided by the product of their norms. Okay, so this could be, I don't know, this could be u, this could be v, or maybe even better, I could call that vector e for edge, d for diagonal, and then modify the formula here accordingly, like this. There we go. Okay. Okay. Now, what are the coordinates? Maybe a good question to ask is, what are the dimensions of this cube? What's the length of an edge? And then we don't have that information. So are we stuck? Now, try to answer this question, okay, before we move on. Now, it's not too hard to see that the angle is completely independent of the length of the edge. So if you magnify or reduce this cube, the angle between the edge and the diagonal will remain the same. So you can pick any length that you want. Now, one good thing in math is to be efficiently lazy. So I like to pick numbers that are easy to work with. Okay, first thing that comes to mind is an integer. And what's the best integer to work with? Maybe the integer 1. So let's assume the edge as a length of 1. So in math we would write something like in our solution, without loss of generality. Loss of generality. Let's assume the length of an edge is 1. 1 what? Well, who cares? 1 meter, 1 centimeter. It doesn't matter. So what are the coordinates of E? Well, E goes 1 unit along the x-axis, 0 units along the y-axis, 0 units along the z-axis. It doesn't go up and it doesn't go along along the y-axis. Well, what's d now? Well, d is quite the opposite. It's now it's going 1 unit along the x-axis, 1 unit along the y-axis, and 1 unit up. So it's 1, 1, 1. So in other words, if you were to associate coordinates to those points, those would actually be the coordinates of the vector, the vectors e and d, because those are position vectors. They start at the origin. And then we're kind of done. Okay, that's the hard part. After that, we just need to apply this formula here. Okay, so after that, all we need to do is, therefore, cos of theta is going to be E dot D. Well, that's just 1 times 1 plus 0 times 1 plus 0 times 1. That's going to be 1, of course, divided by the norm of E. Now, we could add this here if we want, and norm of E, maybe do this computation on the side. Well, what is that? That's the square root of 1 squared plus 0 squared plus 0 squared. So that's, of course, 1, right? And the norm of D, that's the square root of 1 squared plus 1 squared plus 1 squared. That's root of 3. So below here, we'll find 1 times root of 3. So overall, we have 1 over root 3 for the value of the cosine. And then we just take the arc cosine. So if we're in degrees, that will give you, well, I should write approximately. And maybe that's surprising to do. This is some nice angle, actually. It's 54.74 if we round it up. But it's not even a rational number. So it's some weird angle. It's maybe by intuitively you would have thought, well, that's going to be 45, but it's not 45 at all. So that's problem 1. Problem 2, we're going to be given 3 points in the plane, okay, A, B, C, and we have to decide if the triangle ABC, is this a right triangle? Okay, now we'll add the coordinates. The coordinates of B are 0, 4, and 2. The coordinates of C are 2, 1, 0. And the coordinates of A are 1, 2, minus 1. Now try to think about this problem and maybe solve it on your own, and then look at the solution afterwards. Okay, so maybe first thing is consider that triangle here. Okay, and now what we want to do is probably create vectors that are associated to those segments, just like we did in the previous problem when we associated vectors to the edge and the diagonal. So we're going to do that. Maybe I'll write in black. Okay, so now the vector AB, that's vector AB right there, right? AB. How do we calculate it? Well, we do coordinates of B minus coordinates of A, right? So so I'm doing basically OB minus OA, right? You don't need to write that up, and I'm just explaining how that vector AB is obtained. I always know that students sometimes forget how you calculate such a vector. Okay, so B minus A, okay, let's add it. So 0 minus 1, minus 1, 4 minus 2, 2, 2 minus minus 1, so we need to add 1 to 2, so that's 3. Okay, and I'm going to do the same with BC. BC, I would take the coordinates of C minus the coordinates of A. So 2 minus 0, 2. 1 minus 4 minus 3. 0 minus 2 minus 2. And finally, I need AC. AC coordinates are, okay, so C minus A, so 2 minus 1, 1, 1 minus 2 minus 1, 0 minus minus 1, plus 1, like that, okay. So I want to figure out if it's a right triangle. So how do I do this? Now you might remember from a previous video, and maybe I can go back here, that the dot product will tell us when we have a right angle. It's really here when the cosine is 0, when the dot product is equivalently is 0, we've got a right triangle. So what I want to see is if the dot product between a pair of vectors here gives me a dot product which is 0. So I could go and look at every possible pair. Maybe I can be smart about this. I could also think, well, if there's a right angle, okay, let's say I've got a right angle triangle, okay, this right angle here will be opposite to the hypotenuse. And what's the hypotenuse? The hypotenuse is, in a right triangle, the side that has the largest length. So I could also spot the hypotenuse in order to decide which pair I need to vectors I need to test. And how do I find the length of each of the sides? Well, I just need to look at the norm. Now the norm, it's not too hard to see that this will have the largest norm. You can compute the norm. But if this is going to be a right triangle, that's going to be my hypotenuse. So BC would be the hypotenuse in my triangle if it's a right angle opposite to it. So this means I need to test if this is a right angle. So I need to look at AB and AC. That's it. So I've spotted which pair of vectors I need to look at. So I'm going to look at AB dot AC. And that gives me what? This is minus 1, 2, 3. Dot product with 1, minus 1, 1. And when I do this, so minus 1 times 1, minus 1. 2 times minus 1, minus 2. And 3 times 1, 3. And I indeed get a dot product of 0. So therefore, there is a right angle at vertex. So if you're asking yourself what's vertex, vertex is sommet in French, and when you write it in the plural, it becomes vertices. Okay, des sommets. Okay, so we're going to be using this word a lot, and since it's different from French, I thought I'd say something about it. So there's a right angle at vertex A. So it is a right angle triangle. Okay. So that's actually, I don't know if you thought about a different solution. This is solution 1. In the past, I've had smart students giving me a second type of solution. And what they have done is they have verified the Pythagorean theorem. So it's actually true that if you have got a right triangle, that the Pythagorean theorem will hold, but it goes the other way around too. If the Pythagorean theorem holds, it is a right angle triangle. I notice I always write THM for theorem, because that's my abbreviation for theorem. So what we have to do is calculate the norm of actually the norm square. We want to have the length, the square of the length of each side. So I'm going to calculate the norm of BC squared. So basically there's no square root when you square the norm. You just take the square of each of the coordinates and add them up. Okay. And what else do we need? We need so that's BC, right? That's our hypotenuse, the largest norm. And then I'm going to add up the square of the lengths of the other two sides. And if I do this, I get 1 plus 4 plus 9 for AB. And for the other side, I get 1 plus 1 plus 1 when it's squared. And when you add those up, you get 14 plus 3, which is 17. Okay, and therefore AB squared plus AC squared equals BC squared. And bingo. Since the Pythagorean theorem holds, it's a right angle triangle or a right triangle. Pythagorean theorem holds, it is a right triangle. It's kind of a nice solution too. I don't know which one's the best. Well, obviously I like solution 1 because it involves the dot product. But the second one's also interesting because it also uses stuff we've seen in this section. It uses the norm. So both are valid solutions.